Hello everyone, my name is Masagazi Ruth and I'm going to take you through our data warehouse project titled A Semantic Aware Multimodal Data Warehouse for Crowdsourcing Medical Sign Language and Diagnostic Expressions in Uganda. So, Uganda's deaf community struggles to access healthcare because clinics can't interpret Ugandan Sign Language. This leads to misdiagnostics and delayed care. And this project's response is a system that collects, stores, and analyzes medical sign language using crowdsourcing, essentially building a dataset that does not exist yet. Yeah. So take an example that you are deaf and then you go to a hospital, but then you and the doctor can't communicate well. The doctor can't understand what you're saying, and you also can't understand what he's saying. So this can lead to the misdiagnostics and then delayed services. Yeah, so the deaf community continues to suffer. So, and it is not a small population, it is a community whose health outcomes are directly harmed by this communication gap. So this project proposes a solution, which is a semantic-aware multimodal data warehouse that collects, stores, analyzes medical signs and gestures, facial expressions, texture diagnostic data, all gathered through crowdsourcing. So when we say multimodal data, we mean data that comes in different forms. In our case, sign language videos, facial expressions, and written symptom descriptions. And then semantic awareness means the system understands the meaning behind the data, not just the raw input. For example, it can recognize that particular hand gesture or like that represents chest pain rather than simply recording the hand moved. And the data warehouse is a centralized system optimized for storing, querying, and analyzing large volumes of data. Crowdsourcing means collecting data from the public, say students, interpreters, patients, rather than relying on a single controlled source. And a medical sign language refers to specific signs used in healthcare settings to describe symptoms, pain, and diagnosis. And yes, some of the related works, we have healthcare access barriers and the technical contribution of these authors. They recognize the absence of sign language interpreters and cultural competence gaps because that cause misdiagnosis and patient disengagement in the deaf communities. And then another one is AI-driven sign language recognition, where the transformer architectures dominate this whole field. Spatio-temporal feature extraction and the scarcity of diverse video datasets remain primary bottlenecks for clinical deployment. Yeah, and then another one is semantic web and medical knowledge graphs. So recently, the RDF ontologies and SNOMED city facilitate interoperable knowledge. Yeah. So they built an RDF that can be combined with large language models that assists them to map over 93% precision on medical knowledge tasks. This informed our decision to align our data with SNOMED. Yeah, then the problem statement we have, so mainly this project looks at reducing inequalities that this aligns with the SDG 10. And since the deaf communities, as I said, they continue facing barriers to accessing services since almost everything is going digital. So communication is critical in education, healthcare, public services, and the Ugandan Sign Language translation tools that are being created, they must be reliable and they have reduced latency such that they can be trusted and people can adopt to them. And then another one is misinterpretation of symbols. You know, the sign language differs as you go from one region to another. You can find that a sign that is signed in Kampala can mean a different meaning in Gulu. Yeah, and then the computational problem, we have decentralized sources where the data collected from schools for the deaf and health centers, and then the quality variations, the quality changes because there is inconsistent lighting. Someone can record a video in the dark and then another one can create it in daylight. This is going to be different. And since we are looking at training the models on this data, then they have to adapt to this inconsistent lighting, or the videos should be recorded using the same background. Yeah, some of our research objectives, we have our research is guided by 4 questions, and one is, what is the best architecture of fusing gesture, facial, and textual data together? And then another one is, how can semantic awareness enhance diagnostic accuracy? And how can crowdsourcing be effective in Uganda? The 4th one is, how can multimodal data improve medical sign language interpretation? And then some of the objectives, we have we need to implement a lakehouse ingestion pipeline for Ugandan Sign Language telemetry and evaluation outputs, and then model the analytics-ready gold maps using the dimensional design like star or galaxy, and then building dashboards for executive overview, model performance, dataset coverage, monitoring, and drill down, and lastly, to evaluate the platform using metrics, for example, the dashboard query latency, the lag, data quality checks, and the alert for usefulness. And then some of the research contributions we have done and outputs. We have a Ugandan specific, we have made a Ugandan specific medical sign language dataset, but this is made by one interpreter who signed over 489 videos, but this is what we want to break. We don't want to depend on only one signer. We are creating this warehouse to crowdsource data from all over Uganda, from different schools, from different interpreters. And then a semantic-aware multimodal data warehouse architecture, we have come up with one, and a crowdsourcing platform for continuous data collection. It is a mobile application. Yeah, so the methodology and system architecture, it has 2 phases. Our system is built in phases. In phase 1, we ingest multimodal data, that is sign language videos, localized text, and diagnostic notes from schools and clinics across Uganda. Critically, every piece of data is logged with a cryptographic hash in spatial metadata. This gives us what we call epistematic trust at any point. We can verify exactly the data artifact, where the data artifact came from, and confirm it has not been tampered with. And then in phase 2, the extracted metadata, in phase 2, the extracted metadata is cross-referenced against controlled medical vocabulary, specifically the SNOMED City, and against Homo Ugandan Sign Language dictionaries. So this validation step acts as a safeguard against AI hallucination, meaning that incorrect or fabricated outputs from the AI model cannot enter the centralized semantic repository. Only the medically validated data is committed to the system. So on the application that we built, we don't just crowdsource the data and save it to the database. So the person, the interpreter, student, they log onto the platform, they record their videos. After their videos are recorded, we are working with an interpreter who goes onto the platform looks at these videos. If the video is correct, they approve it. But if it is not correct, they decline it, reject it, and then re-record it, because it means if someone took their time to upload this video, it is important. Yeah. Yeah. So for the data set, it is supposed to be collected from schools for the deaf across different regions of Uganda to support Ugandan Sign Language accessibility and standardization. And in the visual layer contains sign language video recording in MP4 or MOV formats that captures words, phrases, expressions along with regional metadata, so we can analyze how signs vary by location. And the linguistic layer contains gloss annotations, written descriptions of what each sign means in the video, and which supports semantic grouping and consistency analysis. And this metadata layer tracks school details, timestamps, approval status, and geographic coordinates, which enables monitoring and geospatial analysis. The bar chart on this slide shows the distribution of schools by region, with central, eastern, northern, and western currently having the highest representations. And we have the knowledge graph architecture. So at the heart of our platform is the knowledge graph. Rather than storing signs as isolated records in a flat table, we organize them in an interconnected network of meanings and relationships. The nodes in this graph represent Ugandan Sign Language signs, their gloss descriptions, regional variations, and the schools and geographic regions they come from. The edges define relationships. For example, sign A represents meaning X, and sign B is a variant of sign A. The structure enables semantic reasoning. The system can identify two signs from different regions that carry the same meaning, group related signs together, and supports semantic search across the dataset. Yeah, this approach reduces data sparsity and improves interpretation accuracy, and lays the groundwork for future AI-driven sign recognition systems. Those are the benefits of using a knowledge graph architecture instead of a relational database that we are saving, that saves the data into tables of rows and columns. Yeah, so these are screenshots for the product, the application that I told you about. It has two panels. We have the admin panel and then the user panel, where the schools, interpreter, and individuals can log on, record their videos, and then upload it to the platform. And then it has the admin dashboard, where the admin can see this overview dashboard, see the schools that have uploaded the signs, and then see the coordinates where the schools are located, and then the actual videos that were uploaded. Yeah, this is the link to the uploaded video of the demo. And then some of the limitations and architectural failure we have. We want to be transparent about the current limitations of our system. So the first is multimodal data quality. Videos are collected, crowdsourced from rural centers. They often suffer from poor lighting, motion blur, which means that the model does not always have enough clear visual information to confidently classify a sign. This is partly an infrastructure problem in Uganda and is partly a challenge we need to address through better data collection guidelines. The second limitation is connectivity. Many of the remote schools we work with have unreliable 3G network, and the world is using 5G. So if we are using 3G, then we are at a disadvantage. So these unreliable 3G connections, which disrupt data ingestion and causes delays in synchronizing local devices with a central cloud warehouse. These are real-world constraints we are actively working to address. Then this part of the 3G and the synchronization of local devices, we are looking at using tiny models that can be used on smartphones, such that if a person is even in the rural areas, they can go ahead to use their phone and then they are not left out. They can use their phone. These models can work on the phones, but it is costly. Yeah. Yeah, for the conclusions and future works, this study rejects a rigid relational database. As I said, the relational databases, they are databases that store data in rows and columns. So we are using the knowledge graph that maps relationships to different signs, that is easier, that helps the model to identify the meaning in the signs. Yeah, so we're using an ontology-driven multimodal knowledge graph. Then the proposed architecture establishes a semantic control plane that harmonizes crowdsourced video data from Ugandan schools and healthcare centers into a coherent structure knowledge system. Yeah. Then the knowledge graph as the core architecture allows us to represent semantic richness and regional variation of Uganda Sign Language in a way that Platables simply cannot. And some of the future works, we are looking at deploying this product using lightweight AI models like the TinyML, as I said, that are directly used on two mobile phones and are used for data collection, removing the need of internet connectivity, favoring the people in the different regions of Uganda. And then the system will be compressed into an offline version that rural healthcare workers can run entirely on their local devices without relying on the cloud infrastructure. Those are some of the references. And I would like to extend our sincere gratitude to Dr. Galiwango Marvin, who's our course lecturer, for his guidance and expert knowledge and continuous support throughout this work. His dedication to teaching and willingness to provide direction greatly contributed to this research. And I would also like to acknowledge my groupmates for their work, commitment, collaborative effort, and the shared ideas, discussions, and mutual support. Thank you.